The fast growth and widespread adoption of artificial intelligence are creating new pressures on global electricity systems.
This is largely due to the heavy dependence of AI on data centers. Large facilities filled with servers that process and store massive volumes of information.
These centers consume enormous amounts of power, making it increasingly difficult for energy providers to maintain reliable and affordable electricity supplies in nearby regions. Most current proposals for handling this rising demand involve building new power plants, upgrading transmission networks, or adding large energy storage systems. However, these solutions are costly, slow to implement, and difficult to scale quickly. A team of researchers and engineers from Emerald AI, working with NVIDIA, Oracle, Salt River Project, SRP, and the Electric Power Research Institute, EPRI, has introduced a different approach. Instead of expanding physical infrastructure, they developed a software-based method that allows data centers to actively support the power grid. Their work, published in Nature Energy, shows how AI facilities can adjust their electricity usage in response to real-time grid conditions, effectively becoming flexible energy consumers. According to Ace Koskin, chief scientist at Emerald AI and co-author of the study, the project was inspired by the growing strain between power grids and the soaring energy demands of modern AI data centers, many of which face long delays in being connected to the grid. Rather than depending on new generation or transmission lines, the team explored how data centers themselves could adapt their behavior to better align with grid needs. At the heart of the study is Emerald Conductor, a control platform designed to manage data center power use intelligently. The system continuously analyzes how much power different AI tasks require and how sensitive they are to performance changes. It then adjusts workloads in real time, slightly slowing down tasks that can tolerate minor delays while keeping critical applications running smoothly. This allows the overall facility to reduce its electricity draw when the grid is under stress, without violating service-level agreements. To validate the approach, the researchers tested it on a real-world AI cluster of 256 GPUs operating in a Phoenix data center. During periods of high grid demand, the system successfully lowered power consumption while maintaining acceptable performance levels. Over a 3-hour window of peak strain on the grid, electricity use dropped by about 25%, with little noticeable effect on users or task completion. This experiment marked the first large-scale, real-world demonstration that AI data centers can function as active partners in maintaining grid stability. By dynamically scheduling and managing AI workloads based on grid conditions, data centers can reduce peak electricity demand while continuing to deliver reliable AI services. Koskin explained that this work moves beyond theory and small tests, showing that grid-responsive data centers can operate in real environments. In practice, this could help AI facilities connect to the grid faster, make better use of existing power capacity, and contribute to a more stable and resilient electricity system. Looking ahead, the team plans to refine the technology and deploy it in additional locations. They are working with industry partners, utilities, and grid operators to test and scale the system under real operating conditions. Over time, they aim to coordinate multiple data centers so they can collectively respond to grid signals, creating a network of AI facilities that actively supports energy sustainability while enabling continued growth in artificial intelligence.